Institute of Engineering and Technology.
Good morning, students. Today we are going to discuss higher order differential equations and its solution process, which is known as general solution, and in that we have seen complementary function, and now we are focusing on particular integral as a second part of general solution. In this part, again, we are focusing on the first method, which is for the special type of functions. We have already seen first case of exponential functions, second case of trigonometric functions, in particular cosine and cos, third case for polynomials. Today we will focus on the fourth category of this, which is known as combination 1. That is nothing but exponential function into some random function. So let us see how to formulate higher order differential equation, how to figure out particular integral in this case. So as usual, this is our second order differential equation y double dash plus c1y dash plus c2y equal to r of x. Y dash and y double dash indicates respectively first and second order derivatives of y with respect to x. C1 and C2 are arbitrary constants and Rx is a random function of x. Now after defining differential operator capital D as d by dx, we can find the operator form of this equation as d square y plus c1 dy plus c2y equal to r of x, and then separating y on the left hand side will give us d square plus c1d plus c2y equal to r of x. This is nothing but f of dy equal to rx. This is known as operator form of higher order differential equation, and this is our first step in almost all solution process. Now let us focus on method which I am focusing in today's talk, which is particular integral for special combination of exponential into random function. That is nothing but our first method, which is direct method, and we know that for particular integral we should take operator form f of dy equal to rx, and by taking y as yp equal to 1 upon f of d into rx, we can take particular integral. Now the next step is depending on rx. Rx can be exponential function, sine or cos, polynomial of x, and then combinations e raised to ax plus b into rx, x plus 2, and into rx. We have seen already first three cases: exponential, sine, cos, or polynomial. Today we are going to discuss our first case of combination. So let us consider this combination. What will happen if Rx is e raised to ax plus b into Rx? This Rx and this Rx, they are not same. This simply means that my right hand side is some random function and in multiplication with some exponential e raised to x plus b. So as usual, I am taking 1 upon f of d into e raised to x plus b into Rx. Now how to deal with this situation? And for that I am taking this e raised to ax outside this 1 upon f of d. So you should write it as e raised to ax plus b dot 1 upon f of d plus a into rx. This exponential function will work as a shifting operator. It will shift your value of d to d plus a. If value of e raised to ax plus b is there in multiplication, your d is shifted to d plus b. But if it is e raised to minus ax plus b, this will be e f of b minus b. Let us see some examples to clear this concept. Suppose I want to find solution of y double dash plus y equal to e raised to x into sin x. Now here the operator form is b square plus 1y equal to e raised to x into sin x. And so the auxiliary equation f of d equal to 0 will give you d square plus 1 equal to 0 m1 m2, which is 0 plus or minus 5. So that is complex roots with alpha equal to 0, beta equal to 1. Now I can take this as complementary function with value e raised to alpha x, which is 0, times c1 cos beta x plus c2 times sin beta x, which is with beta equal to 1. And so answer is c1 cos x plus c2 sin x. Now let us go for the second part of solution, which is 5b. Now here it is 1 upon 1 plus b square e raised to x sin x. So I am focusing right now on this right hand side, and I can see clearly it is my first combination of exponential into some other function. So I will shift this e raised to x outside the bracket like this, and I will change everywhere in this denominator d as d plus a. Now what is value of a? A is nothing but the coefficient of this x in e raised to x. So I am replacing everywhere d with d plus 1. So it turns out to be b square plus 2b plus 2. So now this is this bracket. This is the separate example of our particular integral. This is nothing but the second case of sine and cos. So now I will work as sine and cos on this bracket. So as we know that if our equation is for sine and cos, we need to replace d square with minus of a square. So value of a means coefficient of x in sine x is 1. So d square as minus a square will be d square as minus 1. So replacing this d square with minus 1. So it gives me 1 upon 2d plus 1. Now we know that in sine and cos we cannot convert value of t. We can only convert powers of d which are even. So to generate even power of d in denominator, I am multiplying and dividing by its conjugate. So it is 2d minus 1 in numerator, 2d minus 1 in denominator, which will give you perfect square. So it is 4d square minus 1. Now I can replace this d square with minus 1. So it is 2d minus 1 upon 4 into minus 1 minus 1. So it is minus 5. Taking that minus 5 outside the bracket. Now the remaining part is to multiply this numerator 2d minus 1 into sin x. If I take sin x with 2d and if I take sin x with minus 1, it gives me 2 times cos x minus sin x. This first term 2 times cos x is nothing but 2 times d of sin x. D means derivative of sin x, and so it is cos x. This is how you can figure out solution of any combination which is with exponential function and sin x. Pause and check again each and every step. If you have any difficulty, again revise the video and go through it once again. And so my yt is minus of e raised to x by 5 to cos x minus sin x. Combining it with yc, my general solution would be c1 cos x plus c2 sin x minus e raised to x by 5 to cos x minus sin x. Let us take one more example. Suppose I want to solve y double dash plus y equal to sine hyperbolic x into sin x. Then the operator form is d square plus 1y equal to sine hyperbolic x into sin x. And for complementary function, I am taking auxiliary equation f of d equals to 0, which will give me 2 roots 0 plus or minus I. So value of alpha is 0, value of beta is 1. And therefore, my complementary function is e raised to alpha x in bracket c1 cos beta x plus c2 sin beta x. Alpha is 0, beta is 1. So answer will be c1 cos x plus c2 sin x. Now let us go for particular integral. It is 1 upon 1 plus d square sine hyperbolic x into sin x. Now clearly you can see I can convert sine hyperbolic x into its parallel exponential form. The exponential form of sine hyperbolic x is e raised to x minus e raised to minus x by 2. At this junction, I will also give you formula for cos hyperbolic x. Cos hyperbolic x is e raised to x plus e raised to minus x by 2. So by chance, if you have any example with cos hyperbolic x, you should convert it like that. Okay. So now what I will do, I will take this 2 in denominator outside the bracket. I will multiply sin x along with this numerator. So it will give you 1 upon 1 plus d square e raised to x minus e raised to minus x whole bracket over into sin x. Now taking this sin x along with e raised to x and e raised to minus x. So it gives me e raised to x into sin x minus e raised to minus x into sin x. Now, at this time, I am taking 1 upon d square separately on this first part and second part. So it gives me e raised to 1 upon d square into e raised to x sin x minus 1 upon d square into e raised to minus x into sin x. So that means I have two separate examples of combination. And then in first part, I consider this e raised to x outside. So it will replace d with d plus 1. So 1 upon 1 plus d plus 1 whole square. And in second part, it will replace d with d minus 1. So 1 plus d minus 1 whole square. Now, expanding this denominator will give me d square plus 2d plus 1 and then plus 1 over here, which will give you 2. Over here, it is d square minus 2d plus 1 and plus 1 over here will give you 2. Now again, as it is sin x, I can change d square with minus of a square. A is 1, so I am replacing d square with minus. So over here it is 1 over 1 minus 1 plus 2d plus 2. Again over here, with same change, d square as minus 1, it will give you 1 over minus 1 minus 2d plus 2. Pause and check each and every step over here and then move to the next stage. Okay, so now we have 1 over 1 plus 2d into sin x minus e raised to minus x 1 over 1 minus 2d into sin x. As we know that in sine and cos we cannot convert odd powers of d, so I need to generate even power, and for that I am multiplying and dividing by its conjugate. So it is 1 minus 2d multiplied in numerator and denominator. So it is 1 minus 2d over 1 minus 4d square. Over here it is 1 plus 2d over 1 minus 4d square. So here d square is replaced by minus 1. Here also d square is replaced by minus 1. So it gives you 1 minus 4 into minus 1. So it is 1 plus 4, 5. Same answer over here. So it is e raised to x by 5 minus e raised to minus x by 5, and in first bracket I have 1 minus 2d into sin x, in second bracket I have 1 plus 2d into sin x. Taking this sin x inside this bracket, so it gives you sin x minus 2d sin x. So it is nothing but the derivative of sin x, which is cos x. Over here, sin x and plus 2d means 2 cos x. So finally, after this stage, we will receive particular integral as 1 half in bracket e raised to x by 5 sin x minus 2 cos x minus e raised to minus x by 5 sin x plus 2 cos x. This is how we can find particular integral. Now, combining this particular integral with yc will give me general solution as c1 cos x plus c2 sin x plus 1 half e raised to x by 5 sin x minus 2 cos x minus e raised to minus x by 5 sin x plus 2 cos x. I hope this part is clear now that how to deal with exponential function into any random function. Sometimes it may happen that you have exponential function into polynomial. For example, suppose you have right hand side e raised to x into x. In such cases also you can apply the same technique.
LJ Institute of Engineering and Technology.